Okay. Let me know. Chat working for you guys? Getting some notifications about my upload not being totally great. Let me see. I might turn my... Let's see if I turn my Twitch off. Maybe this will fix it. Turn that off. Can I turn it off? Good. Cool. Nice. Okay. Look at all the resounding chats. Love that, guys. Yes, yes, yes.
That's dope.
Okay, cool. All right, appreciate it. I turn on like the ultra low latency version of it, so hopefully the chats are not like super. Yeah. Twitch to... Oh, internet connections. If I had like an office at UCLA, like a permanent office, not a, I don't know if I'm going to be here next quarter office, I would probably move this whole setup over to there, just because I know I'd have a good connection. If any of you guys are curious about like what it takes to run a streaming setup like this, this is my this is currently what it looks like. So that's all my screens. I got 1, 2, 3, 4, and then a prompter. That's the 5th. And then I actually just added another screen, a little tiny one at the bottom there for if I have a second PC I can run to try to take the CPU load off to just run a dedicated output. But yeah, there's a lot. And I think unfortunately we're kind of getting like a heat wave, which isn't the best because this is done within like a walk-in closet, so it gets pretty hot. I think we're at 77 degrees right now. Okay. Feta Guy says, you make music too? Yeah, I do a lot of things, man. Life has a lot of spices, I say. A lot of spices of life. So, yeah, I do make music. That's actually... So, I have to move Friday's lecture up to 11 because I have to catch a flight to Denver because it's a friend's wedding, but I'm also DJing one of the clubs there as well that night. So, it's kind of like a dual-purpose trip. But we're still going to have lecture tomorrow. I just got to do it earlier to make sure I don't miss my flight because that would be bad. Okay. I'll give another minute for people to hang in, and then we'll hear while we wait. Is everyone finding all the kudu stuff like okay and whatnot? I put an announcement out on Brew and Learn. Yeah, it's okay, Zach. Yeah. I would simultaneously stream to Twitch, but apparently I'm getting like buffering issues, so I gotta prioritize the YouTube right now. It's okay. What club? Beacon is the name of the club. It's in Denver. Yeah, so if you're in Denver and you want to come by and see me, I'll be playing tomorrow night at like 11, I think. One of my many side hobbies. But yes, all right, so let's see. So we had so a new Kudu chapter came out. I made an announcement about this on I made an announcement about this on Brew and Learn. Yeah, that's right. Canvas, whatever you guys call it. But I'm not going to do that every time because we release a new chapter like every 2 days, every 2-3 days. So please, like check this at least once a day so you can see what's up and what's due. I can't really give extensions for pre-lecture questions. For whatever reason, the software won't let me do that. I can put extensions on homework if, you have like some crazy reason that you can't turn in the homework. You get a whole week to do it, though. So, I mean, it's a lot of time. But the pre-lecture stuff, I can't open up new things first. So please make sure you do the pre-lecture. So, yeah, here for periodic motion, that's what we're going to go over today. That's today's topic. That has pre-lecture that's due Friday, so that's tomorrow at 2 o'clock. So, you have like all day today and like most of the morning tomorrow, right, to go do this. I'll remind you again tomorrow for those that come to lecture. But again, it's very easy. just watch a cute little YouTube video, and then at the bottom there's some pre-lecture questions about the video, which should give you an intro into like periodic motion is. So yeah, so that's that. Also, yeah, homework is open for fluid mechanics. So that's due on Monday. That's in 4 days. So try to get that done. I love that people are asking questions on Campus Wire. I'm a big fan of that. This is a great way also for you to like get credit for leveling up on Campus Wire. So yeah, if you have like questions about this, about like, great, I love this. The best way also to demonstrate that you understand a concept is to be able to explain it to somebody else, to be able to like teach it per se. So this helps you guys out as well. So yeah, love this. If you have any questions about Kudu stuff, put it in here. And yes, great. Good job, guys. Yeah, this is great. Love it. Collaborative learning. This is also why I don't curve classes, because if I were to put a curve on a class, it kind of discourages students from helping each other because they know they just need to like beat out their friend, which they're just like trying to beat the bell curve, and I hate that because then you don't like help each other. And like life is all about helping each other, or I think it should be. Also, yes, discussion. I'm letting Albert kind of like run that show on his own. So I'm not sure exactly what he's doing in terms of due dates and submissions. I do know you need to put stuff up to grade scope. So please figure that out because that's how we're going to do the exams as well. So, I mean, the exam isn't for another 2 weeks, I think, or something. So you'll have plenty of more opportunities to get experience with uploading things to Gradescope, but that's important. You want to be able to upload things to Gradescope because the last thing I want to hear is, once the first exam is due, someone's like, oh man, I couldn't upload my test. And I'm like, well, you should have been able to do it because you had like 4 discussions beforehand you should have done it with. So, but I pinned a post here, and Albert's going to edit it and put down the recordings. So it looks like he has Zoom access. Great. Good job, Albert. I think it's because Albert's like an official grad student. I got like kind of like hired in as like a temporary person. So I don't have UCLA Zoom access. That's why we're doing things on YouTube. But he has posted the links here, and I pinned this post at the top. So his recordings will be here, and then my recordings for my lectures will be here as well. So good. That way you guys can complete all the work you need to do asynchronously. You don't have to show it right now, although I appreciate you being here because we can have more direct interactions and correspondence as we learn periodic motion today. Okay, cool. Any other questions? Here, I'll wait like 10, 20 seconds for the stream to buffer. But any questions before we move forward into learning about periodic motion? Okay, looks like everything's good. We'll move forward. Let's do it. All right. Welcome to week 1. I believe this is lecture 4. Lecture 4. Cool. All right. In today's lecture, we're going to go over periodic motion and how that works. So a lot of things in life tend to follow this pattern of oscillating, right? Things go like back and forth. For instance, when you have a mass on a spring, that goes up and down, or it can go left to right. If you live here in Los Angeles, if you go out to the ocean, you'll notice you have waves coming like back and forth, right? That's all periodic motion. And I think the technical definition they have, let's see, what's the technical definition they have for periodic motion? Well, actually, there's a bunch of subdivisions to periodic motion. So you can have like simple, damped, like critically damped, driven. We're going to start off with what just is called simple harmonic motion, SHM. You'll see it in a lot of your classes. They'll talk about SHM, not Swedish House Mafia. But simple harmonic motion is something where the acceleration of the system and therefore the net force is proportional to the displacement, and it acts in the opposite direction of the displacement. So what that means is that the force is a restoring force. And what we mean by that is that the force that acts on an object is always trying to bring it back towards equilibrium. So if you remember from mechanics, so from 1A, right? If I have a block, right? And let's say that this is its equilibrium length. Let's call this like x equals 0. I know that if I were to pull this block, some amount this way, let's say like we pull it like an additional delta x, right? That the force on this block is trying to bring it back towards its equilibrium position, and then that force is equal to negative kx, or we say k delta x. Okay. So the key thing here is, right, if delta x is positive such that, you know, it's to the right, the force will be negative, which is to the left, to pull it back. And it also works in the opposite direction. If I push something in, okay, such that it is compressed, now delta x would be negative, and right, and if that is negative, you get a negative negative, that creates a positive restoring force, or a positive net force. That's trying to bring it back to the right. So here, I'll make like 2 different colors for that. So this would be to the left, and then if you had it compressed, like this would be delta x, which would be negative. And so F would be equal to negative K, like delta x. But if this is negative, then that just equals like a positive Kx. Kind of is what we say. And so that would be a force to the right. Yeah. Okay, cool. So yeah, so that's called Hooke's law. And actually, someone asked me during office hours whether that was, you know, derived from some other concept, or what we say like empirical, I think, which means like it was kind of derived from like experimental observations. This was an experimental thing. Yeah. So it turns out, like, even if we talk about the attraction between like individual atoms and stuff, it's not exactly just Hooke's law. There's other, like, there's Coulomb interactions, and then we looked, and there's like dispersion forces. You probably learned in like chemistry, right? Like ionic forces, London dispersion, van der Waals, whatever. But for the time being, we're just considering springs here, and the restoring force Hooke's law is equal to K delta x, or negative K delta x. Okay. Now, from that restoring force, we can actually, it's a pretty good approximation for covalent bonds. Is it? Oh, okay. I believe it. Yeah, that's more of a, I guess, like a chemistry thing, or maybe even like biology. No, I meant more chemistry. But yeah, springs and stuff, they come up a lot in our world, and I'll show you with other things. It's pretty crazy how most of I talked about this yesterday, right? Where a lot of like the framework of the world seems to like be following patterns. It's the same thing here with like simple harmonic motion. So many things in our day-to-day world follow these rules of simple harmonic motion. And it makes you start to think that, hey, maybe everything's like some big computer program, and like there's like code for it. And I think that's what, you know, the theorists try to do when they come up with like it's called like grand unified theories and stuff. They're trying to find something that connects all of the different types of physics, like quantum, particle, I don't know, gravitational stuff, electroweak. Okay. So yeah, we can come up with, so when things, right, are moving or oscillating, right, back and forth, we can describe that by what's called an equation of motion. So, and these are called like EOMs, right? Equation. When you do upper division mechanics, you're going to use what are called Lagrangians and Hamiltonians to derive these. these equations of motion, which in a summary, what you're doing is you're writing down like all the rules of the system, like all the different forces, all the different potentials, all the different whatever energies, and then from that you can then do some nice fancy calculus in order to determine an equation for where something will be at any point in time. And that's what an equation of motion is. So a lot of textbooks, such as this one, will just dump this on you here. But we're going to go over like kind of where this comes from, because I don't know. I think if you see like where this is coming from, you can start to appreciate it a little bit. So they say that the oscillatory motion of the simplest harmonic motion, which is a block on a spring, has this form. So you can say x as a function of t, so the position as a function of t is equal to the amplitude times cosine omega t plus phi. Oh, you do that in Math 32b. Okay. What is Math 32b? Is that Calc 2 or Calc 1 or Vector Calc? I don't know all the numbers that correspond to things. But yeah, you might do it with if you're doing derivatives and stuff, and that's where this comes from. So, for instance, we remember from it's an extension of Calc 3. That makes sense. Then yeah, if you're doing Calc 3, that's like what is it called? Like Green's theorem, Noether's theorem. There's a bunch of really fancy calculus things, which you end up using in upper level physics to like do some really like cool stuff. Yes, multivariable integration. Cool. That is totally yes. Okay, good. That would be Green's theorem. What's the other one that they? Yeah, there's a bunch of them. Stokes' theorem. There we go. Stokes. That's it. I remembered it. But again, this is the first series of physics classes, so we're not going to get like too crazy with it. But harmonic motion is there. Cool. So maybe you've already seen this before, but for those that haven't, what we remember from mechanics from 1A, right, is that velocity is defined as the derivative of position with respect to time, and then acceleration is the derivative of velocity with respect to time. And if velocity is the derivative of position, then the derivative of velocity would be like ddt of dx dt. And this is the same thing as the second derivative of x with respect to time. Okay. So if you have this as your equation for position, A here, this is the amplitude. Probably remember this from like pre-calc, I would imagine, like high school, right? And that's just like the maximum displacement that something has. If you take a derivative of this, right, the derivative of cosine is negative sine. And then you know from the chain rule, you have to take the derivative of what's inside here, which the derivative of omega t plus phi with respect to t, that just pulls out an omega. And yeah, so what you end up getting is like a omega, which is interesting. They call negative V max. Yes, another way to think about that, yeah. This thing, right, this always oscillates between -1 and 1, right? So you always have, so sine, for example, starts at 0. Oh, but they have negative signs, whatever. It does like this. And so if this is velocity, then the number out front is like the amplitude of the wave, but the amplitude of the wave is the maximum velocity it can occur. So this is also what we say is like max displacement. Okay. And then if you take another derivative, you get the acceleration, which is technically, I guess, it's a omega squared. Because you pull out an omega here when you take derivative, then you pull out another omega here. And cool, they say x max equals a. Phi here is just a phase shift, and that just really just refers to like where along the wave or the sinusoidal curve that you're starting, like where time equals 0. So for instance, like, is this like t equals 0, right? That would be the maximum amplitude, which you could either represent as cosine, right? So you could say like cosine, of 0, that would be like the max amplitude. Or this would have to be like cosine of, I don't know, like omega t plus, what's that going to be, like pi over 2, I think. Yeah, this would be sorry, not cosine, sine. Sine is what I'm going to say. Yeah. So this phase shift just tells you like where time equals 0 along your wave. So this would also be equal to max. This would be your max position. But okay, don't want to confuse people with that. Cool. All right. And then yeah. Oh, cool. Oh, they did write it down here. Right. Yeah. So maximum velocity is a omega. Why are they denoting it as Vmax and Amax instead of just omega squared? I agree. It's kind of, well, they do it down here is what they do. Which like they're being weird with that. It is a good thing to know, right? That whatever number is out front of here is the max position, is the max displacement for position. Whatever number's out here is the max velocity. And then whatever number is outside here is the maximum acceleration. And yeah, they do this. I think it's kind of like backwards to do that. I would have written this, and I would have put these here, and then like done it. But I didn't write this textbook. Fedekai says, "Are we working with physics coordinate system that has phi as the angle spanning the xy plane?" Ooh. So I think you're talking about spherical coordinates in that case. Is that what you're talking about with phi? I feel like that's what you're saying. So S max would be the, yes. I have no clue why they call that. Bro, that's wrong. What? This should not be S max, right? Shouldn't that be A max? The hell? What the fuck is S max? Okay. Yes, that is one second. Let me just go fix that. See, here's the cool thing is that I can go in right now and I can go fix that in the textbook. I'm gonna fix that because that's wrong. Oh, where is it? We just had it. Oh, here it is. Yeah, let's fix that. All right, that's not gonna be Amax. Good. Cool. Okay, that's fixed. There we go. Nice. Okay, much better. Okay, yes, Amax. All right, sorry, let me read through things. Phi is just where you start, correct. It's where you start. It's where time is equal to 0, right? Because look at this, for instance, right? If I plug in t equals 0 into here, right? This all goes away. And so now you have cosine of this. So this is like the starting position in like degrees, like along, or radians really, along the sine wave, right? So for cosine, if this is 0, right? So here, we'll show you like what a cosine function looks like. Cosine looks like this, right? Well, if I could draw things a little bit better. So it starts here, right? So if your phi is equal to 0, then at time equals 0, you would start here, right? This is, for instance, let's say like at t equals 0, and then we're gonna make some cool things here. So this would be your position if phi was equal to 0 in your equation, right? If phi was something else, let's say phi is equal to pi, right? So if phi was equal to pi, that would mean you start here, right? So this would be if phi was equal to pi. So again, this would go away, but then you'd be like, okay, cool. I start at, my time equals 0 starts there. So you would start at like the lowest amplitude of the motion. Yeah. Okay. And then yes, for some conventions here. So T, big capital T here, which I will usually write as like this. This refers to period. And that's the amount of time it takes for one cycle to happen. And then what we learn, the one I always remember is this, is that T equals period, 1 over period is equal to F, which is frequency. And then that omega, which is angular velocity or like angular frequency, is equal to 2 pi F. Fedekai says, yes, but the convention for math and physics is different when it comes to spherical coordinates. It is. dude, that is something that like bugs me, man. Yeah, you're so right. Math and physics have disagreements for like how they measure their spherical coordinates. I'm like, bro, y'all couldn't just like agree on a thing. It's the same thing with if you take chemistry and you start going through like thermodynamics, for instance, the convention for like work being like PDV or negative PDV depends on whether you're in chemistry or physics. Like one of them is like work done by the system and one of them is like work done on the system. Believe me, as somebody who teaches, I teach all science courses. I mean, physics is my PhD and my specialty, but I also teach a lot of chemistry. And it gets really difficult for me sometimes to remember which one we're working with because, yeah, they switch it around. But we'll use the physics convention for phi if we're doing spherical stuff, which we will later with EM. So anyways, this is the important stuff to know for characterizing a wave. I like to think about, period is the amount of time for an oscillation in seconds. And then frequency is like the number of oscillations in 1 second. So period is equal to seconds for one oscillation. And then frequency is number of oscillations for 1 second. That's how they're inversely related to each other. And then omega is 2 pi F, which, yeah, we'll deal with a lot. Okay. With that being said, I think there is a clicker question related to this. So let's go see. Go see what we got. Okay, cool. I do like this, yeah. So, yeah, if you go to Kudu, you should see that there's a new clicker section here, right? Lecture 3 clicker. And this is the first question. It says, a particle is undergoing simple harmonic motion with a frequency as such. Find the second time that the particle crosses x of t is equal to 0. Okay, so here, let's put this down here. And then let me get the answer choices out for you guys. Okay. And there we go. Okay, cool. Here are the answer choices. All right. So the motion, they gave us this. They said that the displacement of something is equal to 4.5 cosine omega t. This is the amplitude, right? So you can see how the thing goes from a maximum of positive 4.5 to a lower of minus 4.5. It's a cosine wave. Cosine waves start at the top and then oscillate. And then there's no phase shift, right? So everything looks hunky-dory. And they want to find the second time that the particle crosses x of t is equal to 0, right? So I see it crosses here. This is the first time. This is going to be the second. That's the one I really care about. All right. And I know that the frequency is equal to 1.5 hertz, okay? But note here, right, that x of t is equal to 4.5 cosine of omega t. So what you have to do first is remember that omega is equal to 2 pi f. So omega, right, is equal to 2 pi times this. So that's going to be equal to 3 pi. So now we can say, okay, cool. So my function is that x of t is equal to 4.5 cosine of 3 pi t. And I want to figure out where this thing equals 0 a second time. So what we know, right, is that if this was a cosine wave, this is kind of like where you're at 0, and then this is what would be a full period, right? So this right here is, I'm going to show you a couple ways you can do this. This is a full period. A period, right, again, is the amount of time for one oscillation. So it's the amount of time for it to go from where it's starting to where it's like restarting again. Key thing here, though, if you were like, for instance, to measure your period from here, this is not a period. You can't find the clicker questions on Kudu? Oh, they should be there. Can everybody else find them? Let me know if you can't. I see it right here. It should say, so sometimes you have to go up to the top here and hit this button, this refresh button, and it should let you. Yeah, just refresh, but don't F5. Don't click F5. Don't do it.
Oh, no.
You'll break the whole thing. Believe me, I've talked to the devs about that. I'm like, yo, guys, can we please get, like, F5 working? And they're like, no, it, like, breaks everything. I'm like, okay. Thank you, Jacob. Thank you, Sib. Thank you, all you guys. Thanks, Aaron. Anyways, so a period is defined as, like, the amount of time it takes for an oscillatory motion to return to its original position, but also needs to be going in the original direction it was. So, for instance, from here to here, it is at the same position, right? 0 and 0. However, here it was going down, and here it is going up. So it is not repeating yet. In fact, we would have to keep doing this until here, and then this would be one period. Because, again, it's at 0 going down. It's also at 0, it's going down. Oh, you're okay. All good. Jasil. If I'm pronouncing that right. I hope I am. Okay. So if this is a full period, right, then I know that this right here would be a half a period. Okay. And then the amount of distance to get to here is going to be a quarter of a period. I can show you a couple ways you can do this. So this is a quarter period, right? 1 quarter period. So, in order to get to here, right, that would be a half plus another quarter. So I know that at here, t must be equal to like 3/4 of a period, right? So you have like 0, 1 quarter, 1 half, 3/4, 4 quarters. And so one way to do that, right, is to remember that, oh, well, period is equal to 1 over f, which is going to be equal to 1 over 1.5 is 3/2. So this is equal to 2/3. And then we want to do 3/4 of a period. Right, so 3/4 of a period is equal to 3/4 times 2/3. So this cancels. You're left with 2 over 4. And so the answer there should be 0.5, like half a second. Good. Abu says, what does W refer to? So W refers to this is called, like, I believe they call this angular frequency. One second. Let me double check that. Omega is angular frequency. I believe that's what we call it. Yeah, it is called angular frequency. Yeah. And I mean, the key difference between that and F is it's measured in radians per second, right? So that's a good point. So omega is measured in radians per second, whereas F is measured in hertz, which is the same thing as oscillations per second, which they really just say is 1 over s. That's the units for it. If you remember from kinematics, we really like to use omega. We don't really like to use F because it just makes more sense for yeah. Good. How do you distinguish angular velocity and angular frequency? So angular velocity. Oh, they're the same thing. Yeah, no, that's the same. Yeah. It just matters it just matters the units they're giving to you, right? So if they give it to you in hertz, right? I know that's a frequency, which is 1 over seconds. Yes, Jacob, another good point. I'm going to bring up, that's another good solution for it. If you see radians per second, then you know that's omega, right? So really just check the units. So hertz is frequency, radians per second is omega, which I call like angular frequency. Angular velocity is a whole other thing. That's something we do in mechanics. I don't think we're really going to do angular velocity in this course. Yeah, I don't think so. Or maybe we will. We will do pendulums, you're right. We might. Okay. Yeah, so that's one way to do it. The other way to do that is to look at the unit circle, right? Completely correct. So if you, for instance, were to draw out the unit circle. This is not a circle. Looks like the Super Smash Brothers logo. There we go. And you were to like move this around, right? Cosine is always like the adjacent side of an angle, right? So in the case of me moving this around, right? The first time it hits 0 is here. And this is at an angle of what we say is like pi over 2. And then the second time that the adjacent component of the angle is 0 is when you come down here to 3 pi over 2. So I know whatever's inside here, I need to equal 3 pi over 2, because that's the second time I'm going to take the cosine of something and get 0. So yes, Jacob's totally correct. The other way you could have written this is that 3 pi t is equal to 3 pi over 2. 3's cancel. Pi's cancel. And you're just left with t is equal to 1/2. And that's in seconds. So both ways work. Those are both legitimate ways to do it. And it's one thing. It's a very good practice to get familiar with like how waves work and working with sine and cosine. It's something that will help you in all of your classes moving forward. It's one of my regrets is that like in high school, I would get panic attacks from sine and cosine. I would just freeze up and ignore it and just like try to like, grin my teeth and just get through it. And if I just like stop to like realize that like sine and cosine are they're just functions that go up and down, and they're only off by a phase difference of 90 degrees. Everything else in physics and math would have been so much more easier. But so yeah, that's my word of advice to you guys is get comfortable with working with sine and cosine. It happens so much. So this question, so 0.5 seconds was answer choice C. So let's check our answer. And that's correct. Cool. Nice. Okay. Good so far, guys? Okay. Let's move forward. Because then eventually I got to get to, yes, energy and stuff. Okay, cool. So, yes. Again, talking about the spring situation, right? Where we had this, right? F was equal to negative kx. You could have also written that out in terms of like F equals ma. So here we go. So if you have some net force, and again, you guys in 32P saying you derived this already. So I'm not going to go through it, but I'll just quickly do an overview. We know F is equal to ma. So that means that ma, so if the net force on a block attached to a spring is negative kx, then F equals negative kx, but F is also ma, so I get ma is equal to negative kx. And then what we remember from up here, right, is that acceleration is the second derivative of position, because it's the derivative of velocity, and velocity is the derivative of position. So then you get this, which you can then rearrange to get here, and this is a classic differential equation. So this right here is a differential equation, and it's a very simple one that we end up solving. I forget the method that's used to actually solve it, but what you end up doing, and I'll leave this as an exercise for the reader, just for time's sake. You get that like x is equal to cosine omega t. And in order to do that, we say that omega squared is equal to negative k over m, or no, omega squared is equal to k over m, sorry. So you can try doing this. You can try plugging this in, and then also plugging in the second derivative, and then seeing that the left side equals the right side. I did it during office hours, but take a look at it if you want. And then from this, right, that tells me that omega for a spring on with a block, omega is going to equal the square root of k over m, right? And then if we remember, right, omega is equal to 2 pi f. So f is equal to omega over 2 pi. That tells me the frequency for a block attached to a spring is going to be 1 over 2 pi square root of k over m. And then the period would be equal to 1 over f. So that's the flip of that. That's equal to 2 pi square root of m over k. And then let's kind of like look at this from like a practical point of view, right? So period is how long it takes, for instance, for this block, right, to go back and forth, left and right, okay? If we look at the math here, right, we see that m, the mass, is on the top. It would make sense, right, that if the mass goes up, the period should also go up, right? So if something's very heavy and it's oscillating back and forth, we would expect that to take more time to oscillate back and forth versus something that was very light. We'll go over this when we go over like sound waves. There's a really cool like justification for this in terms of like how your ear works. Little teaser. And then K, right, is equal, from mechanics, that's equal to the spring constant, or I say like, you know, how tight the spring is. So if your spring is tight, which means K is large, now you're dividing by a large number, that would decrease your period. And that makes sense, because if your spring is stiff or like really tight, then you would expect it to oscillate really quickly, right? It's not going to let it like do this. It's not going to be like loosey-goosey. So just some physical intuition from the math equations. You can always just like go for days deriving math things, but I think it's always important, especially in physics, to like check yourself every once in a while and be like, hey, does this make sense in the physical world? Like, if I increase this amount, what happens to this? Or if I decrease this amount, what happens to this? And does that make sense? And if it does, yeah, then you're probably doing the right thing. Okay. Energy. Yes, let's do energy and the simple harmonic oscillator. Yeah. So, I'm curious if you guys learned this in oh, you did learn this in mechanics, right? We learned that the net work, right, done on an object is equal to it's equal to the change in kinetic energy, right? That's one way to do it. The other thing that we learn is that the work done is equal to the change in the potential. I don't know if I like that. Yeah, they say work is equal to delta U. This is a common thing that that comes up. It's like grad U. We'll do this eventually at some point, but that grad U is equal to F. Yeah, this is cool. This comes up a lot in and this is just a fancy word for like a derivative in all directions. It's called like a directional derivative. You do this also in vector calc, is what you do. But the way we want to explain it is that like also potential. Okay, so if, for instance, from this is actually the real thing I want to do with this is this, yeah. So negative grad U is equal to F. So the gradient, which is the derivative in all directions of a potential, is equal to the force of an object, the force being acted on an object. And what we know, right? So if I'm just doing one direction, so we're just doing in the x direction, now grad just becomes d dx. Like we're going to say for one direction, not like the band. So negative du dx is equal to F. So then you can put the dx over here, and you get that negative du is equal to f dx. And then if you integrate both sides, right, I'm going to get negative, we're going to say delta u, or here, let's say from two different time points. Let's say from time 1 to time 2, and this is from time 1 to time 2. Or position 1 to position 2, sorry. So you would get, yeah, so this is a directional derivative. This is the formal math, the formal math and physics thing that you'll learn. But I'm showing that with this, if we're looking at only one dimension, which is only the x direction, like let's consider just a block, right, that's moving back and forth, okay? That we're only looking at things in the x direction, okay? So this nabla thing here ends up just being d dx. So instead of saying negative grad u of f, I say negative du dx is equal to f. And then I'm moving the dx on both sides. And then I'm integrating. And so this gets me negative, we say like u2 minus u1 is equal to the integral of from 1 to 2 of f dx. Okay. So then let's talk about like what the force is from a spring, right? So for a spring, we have that f is equal to negative kx, right? So this gets me the integral from 1 to 2 of negative kx dx. And actually, sorry, this is like this is x2 and this is x1. We're saying from position 1 to position 2, and then this is like, potential 1 to potential 2. The ones in the subscripts here represent like different situations, like where it's here and then where it's here. So if I'm going to take this integral, right, we know we can pull out the negative k because that's just a constant. So I have negative k, right, x1 to x2. Let me fix that. Just because I know some math people are going to, watching this, are going to get mad at me for not being formal. X dx. The integral of x dx is just raise the power by 1, right? So it becomes x squared, and you divide by the new power. So it's just 1/2 x squared. So this gets me negative k, and then we say 1/2 x squared from x1 to x2, which is the same thing as 1/2 k, so it's negative, and then it's 1/2 k x2 squared minus k x1 squared. Okay. And that's equal to negative, we had here, right, u2 minus u1. Okay, so actually kind of cool. So these kind of like cancel each other, right? And so you get u2 minus u1 is equal to 1/2 kx2 squared minus kx1 squared. Bum, bum, bum. Okay. Okay. And yeah. So what that tells you is that the change in potential energy is equal and opposite to the change in the the change in potential energy for a spring system is equal to the change in 1/2 kx squared. So here's really what we figure out, right? Is that u is equal to 1/2 kx squared. This is the potential energy due to a spring. So for instance, if we had when the spring was at equilibrium, let's say this was like x1 is equal to 0. Sorry, the 1/2 is, yeah, my bad. The 1/2 should be distributed both. And then let's look at a little bit further away. Yeah, sorry, yeah. Yeah, there's a little bit of a latency. It's okay. Here, so here we had x1 is equal to 0. And here, yeah, let's say we have like x2 is just equal to like some position x, right? If we were to look at the potential here, right? So here, u1 would be equal to 0 because this would be 0, right? And this right here would be potential 2. So this is u2 is equal to 1/2 kx2 squared, which is just kx squared. Yeah. Okay, yeah, this is the math definition that you learn for like how to derive what the potential energy of something is due to a restoring force, which is this. We will do this as well when we do electric potential and like electric force, like the Coulomb force. This concept here comes up a lot in physics, and then this is just like a cute little derivation showing how, yeah, change in potential energy is equal to the change in 1/2 kx squared. So here, right, x was equal to 0, so your potential is 0, and then here, x, your new x, right, is a little bit further away, and it's not 0, and that's why now you have a non-zero potential. So the big like take home from this is that the potential energy for a spring is equal to 1/2 kx squared. Now, by conservation of energy, however, when a spring is moving back and forth, we also need to consider the kinetic energy of the object, right? So here's a little diagram showing a bunch of different situations. So if, for instance, you have a spring that is being stretched out at some position A, but its velocity is 0, its total energy at this point is just 1/2 Ka squared. Because remember, potential energy of a spring is equal to 1/2 Kx squared. And then we would say kinetic energy of anything, of any object, is equal to 1/2 mv squared. So here, this is all mu s. Now, as this thing moves back, okay, some of the energy from it being stretched is going to get converted into kinetic, which is why it starts to move. And so here, this is all Ke. And this also refers to what the maximum kinetic energy is. So here, remember that the total energy was equal to 1/2 Ka squared. But here, the total energy has to be the same, which is 1/2 mv squared. So that tells you that 1/2 mv squared is equal to 1/2 Ka squared, where A is the maximum displacement of the block. And from that, you can then derive what the maximum velocity is of something based on what its maximum displacement is and whatever the K constant is. Oh, you also need the mass. Yeah. And then the same thing happens as this thing starts to like then move in, like to compress the spring. Now you start converting more kinetic energy into potential until eventually you have full potential here. So here, let me draw like a little graph of things. Yeah, let's do it this way, just because I like the colors. I feel like it makes visualizing things easier. Let's get rid of this. Sorry, let me move this down. Okay, I'm gonna say that's. Let's do this. Mu. Ooh, that looks weird. Okay, here. Mu s, energy, potential energy of a spring, is equal to 1/2 Kx squared. And then we have kinetic energy due to something moving is equal to 1/2 mv squared. Okay. So, in this first situation, where the object is at rest, but it is stretched out very far. Okay. In this case, your potential energy will be high, but your kinetic energy will be basically 0. Okay. Now, as the object starts moving back towards equilibrium, now your potential energy will start to go down. But because the total energy must be constant, this means that the energy in your movement, your kinetic energy must go up. Okay? So that's these two different situations. It's the same thing as when we had, for instance, what was it, like objects like on a building, and then they start falling down, right? Do you remember, like, you know, if this is potential, if this is kinetic and this is potential, that as it falls down, then the kinetic increases, but the potential decreases, right? And that's why things go faster as they fall down, because you're converting energy that was stored in the height into movement with the velocity. It's the same thing with the springs. There's energy stored in it being either stretched or compressed, and as you go away from either compressed or stretched, you take that energy and convert it into speed, or velocity in this case, I guess. Yeah. Okay. Does that make sense? Sorry, I wanted to like take a second to like come back and explain that a little better. Okay. Cool. So, that being said, we have another clicker question we can do with this, which hopefully should make some sense. So that's that. Good. I'm glad. Yeah. Always, yeah, you know, stop me if things aren't making sense or if I'm going off the rails. I love the feedback. And I will never... I always tell people that, like, there's no such thing as a dumb question in this class unless you ask me what my favorite color is. I would hope you know that by now. But there's no such thing as a dumb question. So please, if it's not making sense to you, I guarantee you it's not making sense to somebody else. And, you know, bringing it up will help the other person out. Okay. But let's try to do this kudu question here, number 2, right? So we're saying that for an oscillating ball on a spring, which statement describes the energy of the system when the spring is at its maximum extension? Okay? So maximum extension... Yes, you're right, Imidai. It is gold. Why is your favorite color silver? No. No, dude. No, it's definitely not silver.
You gotta get in
dude.
the hospital now.
It's definitely not silver. FFD 700. Yeah, that's a good one. Actually, I like I think it's ACF7F. I'll tell you my favorite hex code in a second. I forget what it was, but okay. So maximum extension, that occurs in 2 different places, right? That occurs when the thing is being stretched out the most, pulled out. It also occurs when the thing is being compressed in the most, okay? And in both of those cases, right, we know that's when our kinetic energy has gone all the way down, such that all of our energy can go into potential for like stretching it out or compressing it. So, right, if they said the total energy is 0, well, that's not true. Total energy shouldn't be 0. There's always going to be energy in the potential if it's stretched or compressed. Both kinetic and potential are at their maximum. No, I don't believe that either, right? We know that the kinetic is at 0. And so that's going to be answer choice D here. So potential's at its maximum value because that's what's related to extension. Kinetic energy 0 because I want to take as much energy as I can from my total system and like dump it into extending or compressing. So yeah, correct answer here should be D. Good, got it right. Okay, cool. So then here's another follow-up question, which I think is pretty good here. Which says, the block spring system moves with simple harmonic motion and has an amplitude of A. What is the magnitude of the displacement when the kinetic energy equals 3 times the potential energy stored by the spring? That's pretty cool, right? Okay. Amplitude of A, right? So that tells us... Oh, here, let me get you the answer choices. If you want to use up one of your attempts, like seeing if you're correct before we go over it, totally can. If you want to wait till we get the final answer, all good as well. Okay, so if something has an amplitude of A, right, I know that's going to be its maximum displacement, and that occurs... Wait, where's my picture? Where's my picture of it. Yeah. That occurs here. So this is what we would call maximum displacement, right? That's when this thing has been stretched out the most and its velocity has now gone to 0, okay? So here I have that E tote is equal to 1/2 K A squared, okay? We want to know when the kinetic energy is 3 times the potential. So in order for the potential to go up, right, this thing is going to have to like move in a little bit, right? And as it moves in, it's going to convert this spring energy into also some kinetic energy, okay? So we know E tote here, right? This is 1/2 Ka squared. And we want E tote in like some middle condition. Here, let's say like E tote here for like somewhere in between, right? Because if the thing goes back to its equilibrium position, now it has 0 potential. We don't want to have 0 potential. We want the kinetic to be 3 times the potential. If it was 3 times of 0, that would be infinity. That's too much, okay? So I want, what is amplitude? Amplitude is the maximum distance that this thing travels from its equilibrium position. Equilibrium position is when it's at rest. So amplitude is like how far it comes out, how far it goes in as it goes around this. And what we learn is that's also like this. It's like the peak and the trough of like a sine or a cosine, which is what describes the motion of something here. Okay. So I need this, right, to be equal to spring energy, which is going to be equal to, let's say, like, that's going to be 1/2 kx squared, and then plus my kinetic energy, which will be 1/2 mv squared, right? And so this, which is our spring energy, you can also think max delta in terms of Hooke's law, 1/2 k delta x. Yes. That would be the maximum force that acts on something, yeah. Yeah, not 1/2. Yeah, not the 1/2 though. Yeah, you're good. Okay. So we want the kinetic energy to be equal to 3 times the potential energy, right? So I want this to be 3 times this, okay? So if the kinetic energy is equal to 3 times the potential energy, right? Do you see how that this gets me that, oh, okay. So this is now 3 potential energy worths. And now my E total is equal to 4 mu s. But I also need that E total, right? And remember that mu s is 1/2 kx squared. That also needs to still equal the total energy when it was at maximum displacement. So that must still also equal 1/2 Ka squared. Okay? So we're gonna start seeing some stuff here, right? Now it's just math, okay? So 1/2 cancel. And I'm left with 4x squared is equal to a squared. Right? So that tells me that x squared is equal to a squared over 4. Or if I take the square root of that, right, x is equal to a over 2, right? Square root, square root. Square root of a squared is a. Square root of 4 is 2. So at the halfway position, the halfway amplitude, that is when the potential energy is, when the kinetic energy is 3 times the potential. Good. Yeah. Why do we take a position between 0 and a? Okay. So, good question here. So, we say that something has an amplitude of a, right? amplitude is the maximum displacement, and that occurs here. But when something is at its maximum displacement, it has 0 kinetic energy, okay? So that's why here, this is all just equal to what we say is like, this is all just mu s. Now, as the thing moves back inwards, okay, towards x equals 0, now, right, which mu s is equal to 1/2 kx squared, now as this goes down to 0, your mu s goes completely to 0. But your total energy still has to be the same, which means you must have now dumped energy into kinetic. So here are the two extreme cases, right? So we have when something is pulled all the way out at A, and it has all potential energy. It has like very little movement, very little kinetic energy. And then as this thing moves, yeah, there we go. As this thing moves back inwards, this potential energy from the spring, from it being stretched, goes down. But I need the total energy to be the same, right? So that's why as this goes down, this must go up. And so what you end up getting is here. This is at the 0 position, where now potential energy from the spring has decreased all the way down to 0, and the kinetic energy has gone all the way up to its maximum in order to make sure that the total energy between this situation and this situation are the same. And so we know it has to be somewhere in between when there's a mix of potential and kinetic. Because you see here it says the kinetic energy equals 3 times the potential energy. This means that there's a mix of mu s and kinetic energy. Here, this is all potential. This is all kinetic. All right. Oh, good. Glad me only makes sense. Yeah. So somewhere in between, you have a mix of the two. And so what we knew is that, like, okay, well, if that total energy is a mix, right, then it has to be some amount of potential energy, some amount of kinetic energy. But I know that this thing, the amount of kinetic energy, has to be 3 times this. So instead of writing 1/2 mv squared, I can say, oh, this is 3 potential energies. So it's 3 1/2 kx squared plus this 1/2 kx squared gets you 4 1/2 kx squareds. But that total energy, when it's at its mixed in-between state, has to still equal the total energy when it was at maximum displacement, which is 1/2 Ka squared, because A is the amplitude. So I just set those two equal to each other. And that's when I now solve for x, that gets me that it's A over 2. Which is kind of interesting, right? When you're looking at this, you think, oh, okay, well, if it's all kinetic here, but it's all potential here, maybe halfway it should be 50-50. But that's not right. And it has to do with the potential going as x squared, because it's 1/2 kx squared, right? So it's not linear, right? Potential energy due to a spring is not linear. You don't have half the potential energy when you're half the stretched. I mean, in that case, you have a quarter of it, right? Yeah. Yeah. So it turns out at the halfway point, it's not a 50-50 mix. Good. Could you explain how you replaced the x with A again? Okay. Yeah. So what happened was, so here, right? So this is my in-between state, the green in-between, where we're in between 0 and A. So x is just equal to some x. It's equal to something. Okay. If we wanted to, here, let me change the letter so that we're a little bit more consistent, because I hate saying like x equals x. Let's say here x is equal to c. Okay. So somewhere in between, we're at x equals c. And so at that point c, now your potential energy is equal to 1/2 kc squared, because that's x is now equal to c. It's somewhere in between 0 and A. And our kinetic energy is still 1/2 mv squared, but I know that this is 3 times this, right? The kinetic is 3 times the potential. So the total energy here is 4 US, right? This is a single US. This I know is 3 of these. So US plus 3 US gets me 4 US's, okay? So then that is this, okay? But this total energy here at the in-between state, the green state, has to equal the total energy when we're here, which is when we're stretched out the most, and that's the maximum displacement. And we know that that maximum displacement occurs when x is equal to a. So my total energy here is 1/2 Ka squared, and then it's plus 1/2 m times 0, right? Right. This is plus 1/2 m times 0 squared, because this is like no kinetic energy. But that total energy there, Cameron, has to also equal the total energy at point C when we're in between 0 and A. And so all I'm doing is I'm setting those total energies equal to each other. And then I'm solving, in this case, sorry, let me just solve for what C is. I'm solving for what C is. Bum, bum, bum. And then this is the position. We say, okay, C is half of A. So it's halfway in between 0 and A. You see? Good? Cool. Thanks. Yeah, awesome. Okay. So, yeah. So if we go here, right, half A, that's equal to choice C. So click that. And good, we got it right. Wow. Okay, cool. Let's see. I don't think I want to start another topic because we only got like 2 minutes left, and I fear that I hate rushing through things and then leaving things half baked because then you're not going to remember it. But okay, let's leave it at that. Tomorrow I'll go over circular and circular motion, and then pendulums, gravity. We'll do some damping, I guess. All right, it'll be kind of another full lecture tomorrow. But I want to make sure we need to make sure the fundamentals and the core stuff make sense, because otherwise me teaching more advanced stuff does nothing. Sip says, so we are writing the ratio relationship between KE and PE and setting it equal to the time at its maximum displacement, and this is also equal to a moment in between 0 and A. Correct. Yeah, the moment between 0 and A is where 3 times the potential is the kinetic. Yeah, this is like this right here. This is the in-between. The in-between point. Yeah. Okay, cool. All right. Good. Any other quick questions? Please feel free. You can answer now in the chat, or if you don't get to it, ask on Campus Wire. Yes, awesome. Okay, cool. Yeah, y'all have a wonderful rest of your Thursday. Remember that tomorrow's lecture is earlier. It's at 11 a.m. I know it's an hour and a half earlier. I know if that's too early to wake up, I'm sorry. I need to make my flight. If I don't make my flight, bad things happen. So yeah, come on by if you can. If you can't, don't worry. I will post the recordings, and I'll also give you all weekend to do the whatever, the clicker questions, so that, Anyways, okay, cool. All right. Enjoy. We'll see you tomorrow.
Yeah.